So please get good at mental arithmetic doing decimals and fractions, okay? Otherwise you're a sitting duck, sorry to say. Alright, question 8. What's this one? A continuous random variable x has a probability density function such that f of x equals this for x from 0 to 2 and equals 0 otherwise. Now, given that the derivative of x sine that thing equals that thing plus that, which is a product rule thing, you can work that out easily from the product rule. Then we've got to find the expected value of x. Well, this looks very, very confusing. I think what we should do first of all is work out what is the expected value of x. Okay, now here's our probability density function, so therefore that's what you would have to work out first of all before you really get your ducks in a row here. The expected value of x is that thing, okay, it's x times the probability density function integrated, okay, from 0 to 2. That's what it is. Now, let's have a look and see how we might be able to do that, okay? So that would be, there's our probability density function there. Okay, so basically we're saying here, we're looking for this, okay? We're looking for this, aren't we? Between 0 and 2. Now, have a little look. Have a little look at this. This looks like what we're after. In fact, the integral of this from 0 to 2, okay? So this basically is just a roundabout way of doing integration by recognition, as they call it. So why don't we just take this equation here, rearrange it so that this is the subject, and then integrate both sides from 0 to 2. Woo-hoo. Yes? There she be, guys. Look. Now, you know how to integrate. Come on, you can do this. So therefore, we say that this integral here from 0 to 2 of this thing equals the integral of that, which is just the thing. The integral of the derivative of the thing is just the thing, yes, and then minus the integral of this from 0 to 2. So this becomes an exercise in just crunching through it now. Okay, so what I've done here is I've said, okay, that's the same as on the line below, plus this thing here. I've integrated that thingy there, okay, plus 4 over pi cos of pi x over 4 from 0 to 2. Now, it's just crunch-a-rooney time now. Let's just do it. The definite integrals, okay? And the answer will be ours, guys. The answer will be ours. So, that's 2 sine pi over 2 minus 0, because sine of 0 is 0, plus, now this whole thing with 2 in there, the cos of, yes, look, the cos of pi over 2, which is what you get, cos of pi over 2, with 2 substituted in there is 0, then minus 4 over pi times cos of 0, which is 1. So there you get that, minus 4 over pi. Okay, now this is very simple. Look, sine of pi over 2 is 1. Yes, it is. So therefore you get, that's what you get. And I think that's our answer. Thank you, Mr. Box. Again, now that was nice and easy. If you keep your head and just don't panic about these things. You know, they make them look hard, but they never are. And the answer is never very far away. Okay? Practice is the key and you'll get good at it. Okay? Question 9. Now, what do we got here? Right, okay. Find the value of A. What's A today? Hooray. Oh, it intersects the x-axis where x equals A. Okay, and this is a very simple looking thing. Well, we can work that out. We just make y equal 0. We can solve that, can't we? Yeah? Okay, let's go for it. Yes, that's what f of x equals 0. Now, we just solve that for x, which is a very easy matter. X minus 1 all squared equals 2, therefore x minus 1 is equal to plus or minus root 2. Don't forget the plus or minus, and therefore x will be 1 plus or minus root 2. But if you have a look here, guys, it ain't plus. We're just looking at a restricted domain version of this function here. So we only want the 1 x-intercept here. So a is going to be, what is it going to be? Yes, it's going to be 1 minus root 2. Go back and read the question. where find the value of a. Yeah, that's all right. So a is 1 minus root 2. Woohoo. Yes? All right. Next bit. Okay, now on the axis above, sketch the graph of g of x is the modulus of f of x plus 1 for the same, is that the same domain? Yes, it is the same domain as they had up there, right? Now, all you've got to do is basically modulus it, which means you reflect everything that's in the negative to the positive, where the x-axis is the mirror. Then you've got to make a vertical translation of 1 unit up. Now, and we have to label the endpoints with their coordinates. Well, this endpoint here looks to me to be minus 2 and 7. This endpoint here looks to be plus 2 and minus 1. Okay, that's going to shoot up to there, and then up another one, isn't it? Yes, and this one here is going to go up 1 here. Now let's just show you what I'm talking about. Yeah, there it is. So that's what happens when you basically just do the modulus of f of x, yeah? So that's what I was saying. This point here goes up to there and becomes 2 and plus 1. Then the whole thing translates up 1. Becomes 2 and 2. This one just translates up 1 and becomes minus 2 and 8. Yes? Nice, isn't it? Very nice, very nice. I'm getting excited now. The following sequence of translations, transformations, this is what drives students into total disarray, so pay attention, and I hope I can help you with this. Following a sequence of transformations applied to the graph of the function g. Yes, that's the one we just did over there. Alright, now same domain, everything looks like the same, but we're going to fiddle with what we got on the previous screen. We've got a translation of 1 unit in the negative direction of the x-axis. We've got a translation of 1 unit in the negative direction of the y-axis, and we've got a dilation from the x-axis of a factor of a third. Alright, okay, they're throwing the book at us. Find the rule of the image of G after the sequence of transformations has been applied. Alright, I'm going to do this with two methods. There's the function notation method, which is commonly referred to as Dr. T, and then there's the logical method, which I always prefer because it's basically just logic. The Dr. T method, the first method I'm going to show you, is just basically a cookbook method which can get you into a lot of trouble if they throw anything at you from left field. So I just called them 1, 2, 3 for you, so I can refer to them in the maths which is going to follow here. Okay, this is the function notation cookbook method, otherwise known as Dr. T, DRT, which stands for dilation, reflection and translation. Okay. Now, first of all, we've got this. We've got g of x equals that thing, and what does that come to? Let's substitute f of x in there inside the modulus thingies, and we get this. Now, alright, here it comes. So, that's y, I always put y equals that. Y equals that thing, equals that thing, equals that thing. So now, the first transformation, that the Dr. T, the cookbook technique tells you replace x with x plus 1. It's all reverse logic. So if you're translating 1 unit in the negative direction, you replace x with x plus 1. You just have to learn this, basically, because it's not very logical, not intuitive at all. So therefore what you do is you say, right, therefore I started off with y equals g of x equals this thing. Okay, right? Therefore, I'm replacing x with x plus 1. Therefore, y equals g of x plus 1 equals x plus 1 minus 1, all squared, which just gets you x squared minus 2 plus 1, right? That's the first one done. The second transformation, a translation of 1 unit in the negative direction of the y-axis, therefore we would replace y with y plus 1, right? Now we would get this, see, that's y gets replaced with y plus 1, and that the rest of that is the same, and then you solve it for y. You solve it for y. Therefore you get that, okay, taking one from every of those things. Okay, this one minus 1, this one minus 1 just gets you to there, x squared minus 2 in modulus signs, yeah? Okay, that's that one done. Now, the third transformation, we have to replace y with 3y. If it's a factor of a third, dilation factor of a third from the x-axis, you replace y with 3y, and you get that. Right, you get that. 3y, all of this is still the same, and then you solve it for y, right? And you get y is that, right? You get y is that. So therefore, that is what you're after, okay? Now the huge danger here is, guys, you must never, ever say the image is g of x. You have to use a different y function notation for the image, okay? So therefore you can just say y equals this, that's alright, or you can say if the image is h of x or y2 or something, you can say y2 equals this, that's fine. You can put this in if you like I've just showed you there, because that's actually what the image is. Using g of x as a starting point, you can do that, but you must never ever refer to the image as g of x, because g of x was this thing up here, okay? So that's how you do that, and that's how you do it with the function notation. Nice and quick, but not very logical. It's cookbook. Now this is the one that I prefer, the logical approach. I always use this. Now it's a little bit longer to do, but it bears dividends. You don't get confused, and when they throw something at you from left field, you're still able to cope with it, okay? And believe me, they know how to throw things at you from left field when most people are using this approach, okay? Now let's say that we're starting with any point, x and y is any point on g of x, okay? Now the first transformation takes us from x and y. What is it? Translation of one unit in the negative direction of the x-axis. Now this is logical, so therefore if you started off at x, you would end up at x minus 1 and y, okay? The second transformation, translation of one unit into the negative direction of the y-axis, okay, that's logical too. You would go down 1. You would go down 1 in the y, so therefore that's logical. It's not like this. This is reverse logic over here, where you're doing the opposite to what you're sort of doing the opposite to what you think this really would say. So there's where you end up with that one. Now the third one, where we're doing a dilation from the x-axis of a factor of a third, from the x away from the x, which means we're shooting upwards in the air in the y direction. So therefore we end up with a third of what we had here. Dilation of a third, it's a third of y minus 1. Now that's it. Now I call these end points here where we ended up x dashed and y dashed, right? Now therefore we know that x dashed is equal to x minus 1, and y dashed is equal to a third of y minus 1. Now what I do is I make x and y the subject. You'll see I've just made x a subject here. X is therefore x dash plus 1, and making y the subject here, we're going to say that y would be 3y dashed plus 1. Now that is what I call the key to everything. I put that in an interim box because it is just the key to everything. Because what you now do is you substitute for x and y into our g of x function to get the new image. I call these equations star, and they really are the stars of the show. So just have a look at this, what I'm about to do, and you will be pleasantly surprised, I'm sure, at how easy it becomes. Now, what we had was that y equaled g of x, and it equaled that thing there. Right? Now, what we're going to do is we're going to substitute from the key to everything for x into here, and for y into wherever it occurs, which is here, to get our new transformed image. Okay, so yes, substituting for x and y from equation star, and yes, they are the star, we get this. We get 3y dashed plus 1, which was what y was, okay, equals g of not x but x dashed plus 1, equals the modulus of now x dashed minus 1 plus 1 all squared is just x dashed all squared minus 2 plus 1. Okay, now we solve that for y dashed. We solved it for y dashed, okay? There it is, there. This is our new image, and that's what you get. That's what you get, guys, okay? If you just follow that through, subtract 1 from here, here, and here, then divide by 3, here, here, and here, you get this. Okay, now that is your new image. Y dashed is your new image. That is your new image. That is your new image. Okay. The last thing I normally do is just drop the dashes, and therefore I just say that. So the rule for the image is y equals this equals that. Now you can just say, as I said before, you can just say y equals this, or you can say the image. The rule for the image is this thing equals that, whatever you like, but for heaven's sake, just don't say g of x equals this thing here, because you'd be completely wrong if you did that. Right, so that's how you do it, guys. That's how you do it. There's 2 methods for you. Choose your method. Choose your method. I like this one. I think it's logical, and I like logic. I don't like doing things just by cookbook techniques. That's why I'm a little bit shy of this one. But this is quicker. It's quicker, but you can get into a lot of trouble when they throw things at you with this Dr. T method, so-called, when they put in things which are a bit weird. Like, for example, they give you a transformed looking function, and they ask you to convert that into the original base template function, and you have to use this function notation method. You can get awfully messed up, believe you me, and when you're in an exam setting, that's just exactly what you don't want. So be careful, be careful. You might want to learn both methods, but if you do learn both methods, for heaven's sake, they're so different, you need to learn them both thoroughly inside out and use the one which you feel is appropriate for the situation. Okay? But for me, I'm going with this one every time. I just find it better. Okay? Let's keep going. We're near the end now. Alright, the following sequence of transformations is applied to the graph of the function. Yeah, that's alright. That's what we had before. Now, what are we doing here? We're finding the domain of the image of G after the sequence of transformations have been applied. Yeah, that's alright. We're finding the domain of the image of G after the sequence of transformations have been applied. Alright, well look, don't panic. Don't worry about it. Look, it's very, very easy. Now, we know what the endpoints were, and we're just doing the domain of the image. So we're not worrying about the y bits, we're just worrying about the x bits. That's the first thing to get into your mind. And calm yourself down if it looks hard. It isn't hard, guys. All we're doing is we went from x was -2 to +2, didn't we? Right? There it is there. That's all we're worrying about. So what happens to that point, and what happens to that point? Alright, well look, we've got a translation of 1 unit in the negative direction of the x-axis. So the whole thing's moved to the left by 1. This is a y translation. This is a y transformation. This is a y transformation. Who cares? That we don't worry about 2 and 3. They don't make any difference to the domain. This one does. So therefore, we're just moving 1 unit to the left. That's all we're doing. So therefore, the original endpoints were this and this. We're only concerned about the x ones, the -2 to +2. Therefore, the only transformation which affects the domain of x is the first one, as I was saying. Therefore, look, we go 1 unit to the left, the -2 becomes -3, and the +2 becomes 1. Okay? Now, if you couldn't see that and you got yourself into a flap in the exam, the second method which I used on the previous screen gives you the recipe for x dashed and y dashed in terms of x and y, and it's very, very simple to work out what happens to your transformed points using that key to everything formula which I got on the previous screen. So that's my plug for the logical technique. Alright, now let's have a little rest, and we'll do the next problem. Okay, what do we got here, guys? This is the last hurrah. This is the last hurrah. So, question 10. We've got a function such that from 0 to infinity, including the 0, is this thing. It's 2e to the -x over 5. Yes, that looks about right, doesn't it? We've got a right angle triangle OQP, has vertex O at the origin, vertex Q on the x-axis, and vertex P, yeah, okay, I get that, on the graph of f as shown. The coordinates of P would be, of course, x and f of x, yes, so that all makes sense, doesn't it? Yes? Find the area A of the triangle OQP in terms of x. Alright, the area of the triangle. Well, it's base times height over 2. That's going to be pretty easy, isn't it? Formula for the area of a triangle. So f of x equals this beastie. We're saying that the area would be a half of the base, which is x, times the height, which is 2e to the minus x over 5. That's easy, isn't it? Yeah, that cancels with that. That's very nice. So that's just x times e to the minus x over 5. That's the area, isn't it? I think so. Yes, very good, Mr. Box. Thank you. That was nice and easy, wasn't it? We were looking for something very hard. Oh, probably they're going to give us something hard in a minute, but don't worry, we can do it. Find the maximum, oh, here we go, it's a maximum minimum thing. Find the maximum area of triangle OQP and the value of x. So therefore dA dx is by the product rule. Left d right plus right d left. Does that make sense? That's left is x, the derivative of the right is minus a fifth of that thing, plus the right, which is e to the minus x over 5 times the derivative of the left, which is 1. And we just need to simplify that a bit. That looks interesting. Now we've got to set that equal to 0, knowing that this beastie here can never ever equal 0, can it? You have a look at the graph of e to the minus x and you will agree with me. It never ever gets to 0. It approaches it but never gets to it. So, alright, so we can say if that's the case, we know that that must be the one that's 0 by the null factor law, and solving that for x, yes, we know. Therefore, solving that for x equals 5, and that keeps us alive, doesn't it? So now, find the maximum area. Okay, going back to the question, find the maximum area, we just have to plug that into this formula here. And yes, thank you. So x is 5a is going to be, is that right? 5 times e to the minus 5 over 5, which is e to the minus 1, which is 1 over e. So therefore a is 5 over e. A max is 5 over e. Thank you, Mr. Box. That's very nice, isn't it? Well, that was pretty easy too. Goodness, where's the hard stuff, guys? Huh, this must be it. This is the last one. Right, so let's see what they're asking us here. Let S be the point on the graph of F on the y-axis. Oh, here, on the y-axis. Is that right? Yes. Let T be the point on the graph of F with the y-coordinate of a half. Yes, all right. Find the area of the region, this shaded region here. Yeah, okay, that's all right. We can do that, can't we? Now the question is, don't rush in where angels fear to tread. Just have a look at it, size it up, and look for the easiest way to do it. Now, the easiest way to do it, well, you could try and mess around and get the equation of this line if you wanted to, which I would not recommend. And then do, you know, this y2 minus y1 bit from here to here. You'd also have to find out this point here, the x coordinate of this point here, so to get your terminals for your integrals sorted out, because we have to get the area, don't we? You know what I would do, guys? I wouldn't do it using the equation of this line. I think that would be too long-winded and just too traumatic at the end of an exam. I'm going to work out the area of a trapezium. Okay, that's what I'm going to do. From S to T to here, and back up to there, that trapezium. And then I'm just going to minus from the area of the trapezium the area under the exponential function here, from 0 to whatever this value of x is here. And I think that's going to be a much easier way of doing it, actually, between you and me. So let's just go with it. Okay, f of x equals that. Yes, okay. Now, when x is naught, we've got f of naught equals 2, and we've got when x is a half, we've got, here we go, when f of x equals a half, I'm solving this for x now, so therefore I'm saying that that makes sense, and therefore if you take the log of both sides, you'll get minus x over 5 equals minus log of 4, or log of a quarter, which is minus log of 4. Therefore we get x is going to be 5 log 4. Okay, so that's the x coordinate at point A, guys. Okay, happy? Good. Now, here we go. Area of a trapezium. That's the trapezium O to S to T to A. Have a look at it. Is basically the length of the parallel sides, add them up and divide by 2, the average length of the parallel sides. So basically this up to here is 2. This one up to here is a half, so that's 2.5 divided by 2 times the x coordinate, the length from O to A is 5 log 4, and we've got the area of the trapezium. So what is it? 5 over 4 times 5 log 4, which is 25 over 4 log 4. Right, we've got that one sorted out. Now that's a major milestone. Now we have to do the area under the exponential curve. Okay, so what is it? It's the integral of 2e to the minus x over 5 with respect to x from 0 to 5 log 4. Okay, now over the screen we go. Now this is just crunch-a-rooney now. Just be careful, don't lose it now. It's easy from now on. We've basically demolished this question. Okay, just by taking stock, working out the best and easiest way to do it so that we're less vulnerable and less prone to error. Okay, so integrating, we get 2 times 1 over negative a fifth, e to the minus x over 5 evaluated from here to here. Okay, so what does that come to? It comes to minus 10, that's right, excuse me, minus 10 e to the minus x over 5 evaluated from here to here. Yes? Yes, you still with me? Alright, now this one, this upper terminal is likely to give us the final little bit of trouble, but it won't give us any trouble because we know what to do. We know what e to the log something equals. So that comes to minus 10 e to the minus log 4 plus, because this here is already a minus, alright, so don't get confused about that, plus 10 e to the 0. Alright? Now, what would you do with that? What would you do with that? Well, I know what I would do with it. Yes, that's what I'd do with it. It's log plus log of a quarter. You have to get it as plus log of something before you can basically say e to the log something equals to something. Alright? So basically, this now is just exactly what we want. E to the log of a quarter is a quarter, guys. So therefore it's minus 10 times a quarter plus 10, which gets us 10 into 1 minus a quarter, or 10 into 3 quarters, which gets us, is that right? Yes, yeah, 5 over 2 times 3 is 15 over 2. Now, the trapezium minus the area under the curve is that, and that is our answer. I know, it's mighty fine, and we cleaned up, guys. That is the exam done for you, okay? So you go back and have another go at it, and understand absolutely everything I did. If you don't get it, have another look at the video. And, okay, all the very best to you, and have fun with it.